Today we are going to learn about the anti-log amplifier. This is the anti-log amplifier circuit, and before going into the details of the anti-log amplifier, let us just do a quick revise on the log amplifier circuit. Here is the log amplifier circuit. So this is the op-amp and here is the transistor connected, and the non-inverting terminal is connected to the ground. So this point is 0 volt. So this is also 0 volt according to virtual ground property. So this is 0 volt and this is connected to the collector, that is the collector is grounded and the base is also grounded. So the only voltage here is the voltage between the base and the emitter, that is VBE. So since transistor is a 3-terminal device, and here since these 2 terminals are grounded, this acts as a 2-terminal diode. This becomes a 2-terminal device called diode. So we use the diode equation in the coming derivations, in both of the derivations, in log amplifier as well as the anti-log amplifier. So let us jump right into the anti-log amplifier part. So here it is. This is the anti-log amplifier circuit. This is nothing but if you know log amplifier, we can also write anti-log amplifier easily, because the circuit consists of 2 log amplifier circuits with some modifications, a voltage divider network as we can see here. And here the differences are, the first transistor is connected to the emitter of the first transistor is connected to the emitter of the second transistor as well as to the output of the second transistor, and here the output is taken as V0, and here the base is connected to the voltage divider network. So VB is the voltage due to the voltage divider network, and we give this point the name VA, that is the voltage between the emitter, this emitter and this emitter, that is VA. Okay, and we know that since op-amp takes no current inside, it has infinite input resistance, IC is coming through this one, no current is entering op-amp, and the whole of the IC goes into I, that is IC equal to I. Okay, then you can see 2 resistors, R2 and RTC. RTC is the temperature dependent resistance which is used to compensate the temperature losses, which was as explained in the previous lecture. Okay, now we start the derivation. We first start off by writing VB. What is VB? It is the voltage at this point due to the voltage divider network. Okay, so VB, it is the voltage here. VB is equal to Vin, supply voltage, into RTC by R2 plus RTC, since it is the basic voltage divider equation. Okay, now we have to write VQ1B. So you must be wondering, what is VQ1B? Q1 is the first transistor and Q2 is the second transistor. So VQ1B is the base emitter voltage between the first transistor, and VQ2B is the base emitter voltage between the second transistor. So we are going to write about VQ1B. What is VQ1B? Okay, we know that this is VQ1B and this is VA. If we write KVL, we can see that VA, this is plus, this is minus, since current is going this way. We can see that VA plus VQ1B equal to 0. That is VA plus VQ1BE equal to 0. So VQ1BE equal to minus B. Okay, so VQ1BE is equal to minus V. Now we are going to write the diode equation. Okay, what is the diode equation? I is equal to I0 into e raised to V by Vt, where Vt is equal to Kt by Q, which is the temperature equivalent of voltage, and I is the current through the diode and V is the voltage through the diode. So here we are talking about this one VQ1BE, and there the current is IC or IE, since IC equal to IE. So since it is of the first transistor case, we are taking IC1 or IE1. So we are going to write IE1 is equal to IS into e raised to QVQ1BE by KT. This KT by Q comes in here. That is why it looks in this way, where IS is the reverse saturation current. Okay, that is, this is equal to, since IE is equal to IC, IC1 is equal to IS into e raised to Q VQ1BE by KT. From this we are going to write IC1 by IS is equal to e raised to Q VQ1BE by KT. Okay, you guys are with me now? Okay, now we are going to, since to remove this e raised to term, we are going to take the logarithm. This is natural logarithm. So ln IC1 by IS is equal to Q VQ1BE by KT. This e raised to just vanishes and only this term remains here. So we are going to rearrange this, and we can write VQ1BE equal to KT by Q into ln IC1 by IS. Okay. Now we are going to write what is IC1. Let us look at IC1. IC1 is the current through the resistor R1. So according to Ohm's law, I is equal to V by R. So what is the voltage here? Voltage across this one. Here the voltage is 0, and here the voltage is V0. So we can write IC1 is equal to V0 minus 0, that is V0 minus 0 by R1. So we write IC1 is equal to V0 minus 0 by R1, which is equal to V0 by R1. So we put this into this, and we can say that VQ1BE is equal to KT by Q ln V0 by R1 into IS. This is denominator, this 2 comes in the denominator. Okay, now we are going to talk about VQ2BE. Similarly, then VQ2BE is equal to KT by Q ln, instead of V0, when it comes here, the voltage here is V reference, not V0. Unlike this part, V reference minus 0 by R1. So here it becomes KT by Q ln V reference by R1 into IS. Okay. Now we wrote earlier that VQ1BE equal to minus VA. So we write VA here minus VQ1BE, and we found out VQ1BE just now, which is equal to minus KT by Q ln V0 by R1 into IS. Okay, now we are going to talk about VQ2BE. So the thing is that we are introducing VA and VB terms into the equations, and with the VQ1BE part and VQ2BE. So now we are going to write VQ2BE in terms of VB and VA. So now we look at the figure. When we look at the figure, we can see that VB minus VQ2BE is equal to VA plus minus. So we can say that VB minus VQ to B is equal to VA. So we are going to write here VB minus VQ to BE is equal to VA. So VQ to BE is equal to VB minus VA. That is what we wanted. So now we have found out VA and we have found out this equation. So we are going to write this. We know what is VQ to BE. KT by Q ln B reference by R1 into IS equal to, what is VB? What is VB? That is what we found out in the first place. VB is equal to V into RTC by R2 plus RTC. Remember, this is the VB is the voltage. I told you VB is the voltage due to the voltage divider network, and that is what we found out in the first place. So we put it here. V in VB. That is, instead of VB we write V in into RTC by R2 plus RTC and minus VA. That's already one minus, so minus become plus KT by Q ln V0 by R1 into IS. Okay, now we rearrange this. We put the two terms that have ln on one side, that is, we take KT by Q outside. KT by Q ln V reference by R1 IS minus ln V0 by R1 IS is equal to V into RTC by R2 plus RTC. Okay, now we know ln A minus ln B is equal to ln A by B, so KT by Q ln V reference by V0 is equal to V in into RTC by R2 plus RTC. Okay. Now we are rearranging this. When we bring this V0 to the numerator, it becomes minus KT by Q ln V0 by V reference equal to Vn into RTC by R2 plus RTC. Okay, now we again rearrange this. We know ln V0 by V reference is equal to minus Q by KT RTC by R2 plus RTC. You understand what I did there? I just brought this KT by Q to this side. Okay, now except when there is V, sorry I forgot to put the V, and all this is a constant. Okay, RTC, R2, RTC, and we put all this as K. Even if you include the minus in it, it is still a constant. Now I am just not taking minus. Even if you take it, it's the same thing only. So ln V0 by Vf is equal to minus K into V. Now to convert ln into log, there is a way. Log 10 to the base x is equal to 0.4343 ln x. This is useful for gate exams also. You have to remember this. This is important. Okay, now if we want to convert this to log, we write log to the base 10 V0 by V reference is equal to minus 0.4343 into K into VA. And this is also a constant, since put it as K dash. Okay, so log to the 10 V0 by V reference is equal to minus K dash into V. V0 by V reference is equal to, that is we are taking out the log term, so we take exponential 10 raised to minus K dash V. Okay, that is V0 is equal to V reference into 10 raised to minus K dash V. That is, this has now become an exponential term or an antilog term, and thus we get the output in the antilog terms of P. That is, output is gained as the exponential term of input. So this is the antilog amplifier output voltage equation. And with this, I am concluding this tutorial. Thank you.